welcome back. Today we're going to be looking at Millikan's experiment. I'm going to also leave a link so that you can get maybe a better visual with a video. But essentially, there was a guy basically just over 100 years ago where he discovered the charge of an electron. And I already mentioned what that charge was at 1.6 times 10 to the negative 19 coulombs. But he devised this crazy experiment in which he was able to figure that out with multiple trials. But essentially what he did was he set up two parallel plates, one that was going to be positively charged, one that was negatively charged. He ended up throwing some oil droplets into the air. Some of them went through this little hole over here. And then he kind of measured the velocity at which they traveled. So some of them would either be going down, depending upon the field. As you change the field, some of them would sometimes go up. And then there was the unique case where they would actually be suspended. And the question arose, and well, how in the world can you get something to be suspended? And we're going to be taking a look at a couple examples of what that is. And so before we go on, though, I just want to point out over here, these are some, I guess, drawings that I drew before showing an electron or something that's negatively charged within this field here. And we already mentioned that if you have an electric field that is pointing downwards, so going from the positive side to the negative side, the electron is going to be going in the opposite direction to the field. Now, if that was the case, you had a negatively charged object, you have an electric force upwards, which opposes force of gravity. So if you're able to have something that is kind of stationary, not moving either up or down, what you would be able to say is that the electric force is actually equal to the force of gravity. All right, let's look at a couple examples now. We're looking at Millikan's experiment here. So we have two parallel plates in a uniform field, electric field. Here we have an oil droplet that has a particular mass of 2 times 10 to the negative 15 kilograms. It also has a charge of positive 2 electrons. And so denoting EC as an electron, or later on I write E to the negative as an electron. Anyways, this positive 2 is telling us that we have a positive charge here. And so I wanted to determine what is the charge right away. So I took 2 times whatever the charge of an electron is to determine, well, how many coulombs do I have of charge in total? This value is a positive value. Knowing that it's a positive value and we have a particular electric field, I already know that my force is going to be in the same direction as my electric field. And so that force, my electric force, is going to be upwards because my electric field over here is up, so is my electric field. And the question that's being asked is, well, what's the acceleration of the drop? And so after determining my charge, I went over and determined, well, what's my F net? And the forces involved are the electric force going upwards, but then the force of gravity is opposing it because force of gravity is down towards the Earth. And so I end up having Fe minus Fg is always, the F net is always equal to Ma. So in this case, this also equals Ma. I rearranged the formula and then I plugged in my values. Keep in mind when you're typing this in on a calculator, make sure that you put your brackets in the proper locations there. Otherwise, you may in fact get the wrong answer. After plugging in my values, I got 12.7. When you round to two significant figures, which is what is represented by these two values, this value, you're going to get 13 meters per second squared, and you need your vector upwards. Whoops, I almost forgot to tell you how did I get Fe and Fg. Well, Fe, the formula, is equal to charge times electric field, and just plug in those values and get an answer from there. And similarly, our Fg is equal to m times g, and was given in our question right over here, and just multiply that by 9.8. And that's how you get the Fe and the Fg. All right, number 2, an oil drop with a charge of positive 3 electrical charges here is in an electric field of 240,000 newtons per coulomb, again facing up. It is held in balance. What is the mass of the drop? So this time there is no acceleration. And again, the first thing that I did was I determined, well, what was my complete charge? So this time it's 3 times 1.6 times 10 to the negative 19. And again, this positive 3 represents our positive value. And so we have a charge of 4.8 times 10 to the negative 19 coulombs. After doing that, I again went to say, well, what is my F net equal to? What are my forces? Well, if it's a positive charge in an electric field that's facing upwards, my force is also facing upwards. And so my electric force upwards is going to be equal in magnitude, opposite in direction to my force of gravity. So these two are equivalent to each other. Then you just break them up into their equations. Fe is equal to QE or EQ, and Fg, force gravity, is equal to mass times gravity. Rearrange our formula to determine what the mass is, and then just plug in your values. And the same thing, all these other values over here are either given, and the only one we had to calculate was our charge over there. And lastly, for number 3, what electric field is needed to keep a drop with a charge of negative 5 electrons and a mass of 8 times 10 to the negative 14 kilograms in balance? So bear in mind, this time we're dealing with a negative charge. So when we go negative 5 times the charge of an electron, we're going to get a negative value over here. And just keep in mind that now our force and our electric field are going to be in opposite directions to each other. So again, we're setting them equal to each other. Why? Because it's in balance, so there's no movement, so that our electric force and our force of gravity are going to be equivalent to each other in magnitude, opposite in direction. Rearrange it, so this time we're looking for what's the electric field equal to, and plug in your values and get an answer. And so over here, what you're noticing too is that the charge is that negative 8 times 10 to the negative 19. We're going to get a value of negative 980,000. And you can either write it like that, or preferably where you're going to mention, well, what direction is that facing? So we have 980,000 newtons per coulomb downwards. So hopefully that should make sense, that the electric field is facing downwards, because remember, our initial electric force was upwards. And remember, when you're dealing with that negative charge, you're going to have opposites for your electric force versus your electric field. So that concludes the Millikan's experiment. Now it's your turn. There's a couple questions for you in the problem, so get at her. Let me know how it works. Thanks.